Today we will be discussing an important topic called the diodes. So, you all know what a diode is. Okay, let's see. See, you all know this device. This is a resistor. So, it allows current flow in both directions. That is from this direction, from here to here, this way or this way. So, this allows current flow in both directions. Now, this is a diode. The main difference between these two is the diode allows the current flow only in this particular direction. So, this arrow, the diode, the symbol itself is marked in such a way like it is showing the direction of the current flow. Okay, now we will see the voltage and current characteristics, VI characteristics of both. Now suppose, see, this is the VI characteristics of a resistor. So in the resistor, whenever we increase the voltage, the current also will increase that in a linear fashion. See, that is why the graph is linear. So it's easy to find the voltage and current at different points. Suppose for this voltage, this is the current, but in the case of a diode, this VI characteristics, it is not linear, it is non-linear. We can see that. So it is difficult to determine the current and voltage at different points. Not that easy as compared to the resistance VI characteristics of a resistor. So for this, we use some methods called approximation and equivalent circuit methods to calculate the voltage and current at different points. So first is the ideal case. Ideal case is like, we can see this is a diode and we have applied a voltage, and the positive voltage is applied to the side of the diode. This is the anode side of the diode and this is the cathode. So I am applying a positive charge to the anode side, then that condition, and negative to the cathode side. In that case, the diode is said to be in forward bias condition. So a current will flow, you can see the green color. So, and I apply the voltage, even a small amount of voltage also, the current will flow. In the ideal case, whatever, even if it is 0.1 or 0.001, whatever the current, whatever minimum value also, if we are applying, the current will be flowing. This is what we assume in ideal case. Okay, and we will be getting the current and voltage at different points, right? And you can see we can see in that VI characteristics, even a very small amount also, the current starts increasing, so it will increase the VI characteristics. Then in the reverse bias condition, this anode, this is anode and this is cathode of the diode. So this is connected, this anode is connected to the negative terminal and to the positive. So in this case, what happens, this is in reverse bias and no current flow will happen. So in this case, the VI characteristics will be like, we will be applying the voltage in this negative direction, and there is no current flow, just the voltage is increasing. Okay, so and this is the combined VI characteristics of both forward bias and reverse bias. I hope it is clear. So in order to find voltage across this diode, we can use Thevenin's equivalent between the two terminals. So these are the two terminals. So this is the first terminal and this is the second terminal. So we can take this particular diode outside of the circuit and find Thevenin's equivalent between the two terminals. Okay, since it's an ideal diode, it will be 10 volt across both sides of the diodes. Sorry, if we apply, this is 100 volt, so it will be 100 volt here, and here also it is 100 volt. So 100 volt here and 100 volt here, because it's an ideal diode. Whatever is voltage is applied, it is flowing through it like that. So it will be 100 volt in this case. Now we will do the first approximation. We should know, like, every diode has a certain. So in this case, in the first approximation, we take into the concept called threshold voltage. So in the ideal case, we assume that even a very small amount of current we are applying, even if it is 1 or 0.1 or 0.01 or 0.001 or 0.00001 of voltage, then also the current is flowing. but in reality that is not the case. So we have to apply a particular voltage. There is a particular voltage and we have to apply a voltage which is greater than this particular voltage. Then only the current will starts flowing in that particular diode, and that is different for different diodes. For example, silicon, if you take the case of silicon, that particular voltage is 0.3 sorry 0.5 no, zero point 0.6 and 0.7, 0.5 to 0.6 you can say. So suppose and for germanium it is 0.3, and if silicon, let's see, it is 0.6 in silicon, so I have to apply voltage more than 0.6 volt for the current to pass through the diode. So that is the case. So we take in the first approximation, we will take into consideration of this what this concept called the threshold voltage, that is the minimum voltage above which the minimum, it is the minimum voltage, so above which the diode conducts, okay, or the diode allows the current to pass. So in ideal case we didn't assume it, so this concept of threshold voltage we are applying it. So what happens here, see, we are applying the voltage, nothing is happening, and it reaches VT. Suppose the atom is silicon, and 0.6 is the threshold voltage of silicon. Then if we are increasing the voltage, and when it reaches this particular point for silicon, that is, this is 0.6, then no, the current will start flowing. So whatever, again, if you are continuously increasing the voltage, no, there won't be an increase in the voltage, only the current will increase. So this is a maximum voltage you can apply, so the current will start increasing. Then in the reverse bias condition, no, in the first approximation also, when we are increasing the voltage, there is no current flow, it is just voltage we are increasing, but there is no current flow. So we can see the equivalent circuit of this. See, this diode is in forward bias. See, positive charge to the anode, so it is in positive forward bias. So its equivalent circuit will be like, see, positive biased diode means it will conduct electricity, the current will flow through it. So it is like a closed loop. See, it is like a closed loop, and the positive is connected to the positive terminal of the diode. We can replace it with a battery like symbol. See, and this is the threshold voltage here, that is 0.7. Suppose this is a silicon conductor, then the threshold voltage will be 0.7 volt. Let it be 0.6 or 0.7, whatever it is. So it's 0.7 volt we can assume, and the resistor is there 100 ohms. So the current will be equal to the difference V, the total voltage will be V applied, this is a 10 volt, minus this Vt by the resistance, which will give you the more accurate current. But in the case of no, reverse bias diode, the equivalent circuit will be like, see, since this won't allow the current flow, we can represent it with an open circuit. Sorry, yeah, so open switch we can say. See, so this is how we can represent it. So after reaching the threshold, if you apply more voltage, then only current will increase, and the voltage remains at the threshold voltage. This I have already told you. Then in the reverse bias, when voltage is increased, and there will be a point will be reached, and then current starts flowing, and this particular point is called the breakdown point, and that particular voltage at which this happens is called the breakdown voltage. That point is called the breakdown voltage. And we say like diodes should not be operated in this region, specially designed diodes, they are called Zener diodes, they can be operated in such regions. Then we can go to the second approximation. So in the first approximation, first we took the case of an ideal diode, and the first approximation is like, we thought like we made like every diode is having a particular threshold voltage. We have to apply a voltage above the threshold voltage for that particular diode to conduct. And the second approximation, we see like every diode, first we saw like every diode has a threshold voltage in first approximation. Here we see like every diode has a resistance. In first approximation it was threshold voltage. Here we say like it has a resistance called the bulk resistance or the body resistance. So once we are increasing the voltage, and as the voltage crosses the threshold voltage, then the current will flow. This is what we told earlier. So once the voltage we apply it crosses Vt, then the diode will also start offering some resistance. So by the second approximation, it means like we should take into account of this also, this extra resistance also, which is put forward by the diode. So in that case, the current will be the difference of the two voltages, that is the applied voltage minus the threshold voltage, by the resistance which is already in the circuit plus the resistance which is offered by the diode, that is the bulk resistance or body resistance. So this is the case. And in the VI characteristics, no, we can see like if instead of that it was going straight, here there will be a bend like this due to this. If you like, see, and this is the you can say piecewise linear details. So we can see the full here. See, first case we can see like in the during forward bias, we are applying the voltage. It is reaching a particular voltage called the threshold voltage. From there, the current starts increasing. So this is the forward region of operation of the diode, and this is the reverse region, and this is the breakdown region, and the current which flows through this particular reverse region is the reverse saturation current. So that's it.